Welcome to our channel again, Suraj here, and today we are going to discuss about the Lagrange equation, which is a more fundamental equation than the D'Alembert principle. Why? So we are going to discuss in this video, and also the applications, maybe the derivation of this particular equation in the next video. But for now, its applications and what exactly is the Lagrange equation and why it is more fundamental than the D'Alembert's principle. So let's start our today's video. So in our previous video, we have discussed about the D'Alembert principle, and if you're interested in knowing about that, you can watch my previous video. I will put down the description box about that link. And why there is a need of the Lagrange equation first of all. So first of all, you have to write out the D'Alembert principle, which says like this particular equation that Fi and minus Pi, and there is a Pi dot which represent the time derivative of the momentum I've discussed in the previous video, and the del Ri is equals to the 0. So this is the principle of this is the D'Alembert principle. But as you can see that Lagrangian equation is mainly based upon the generalized coordinate, and in this particular D'Alembert principle there is a not a generalized coordinate but a general Cartesian coordinates which can lead to different types of the difficulties while solving the advanced problem. That's why we want an equation that is independent. It means it only contains the generalized coordinate, not any type of these particular Cartesian coordinates. That's why we need an equation, and that equation is called the Lagrange equation. So the general form of the Lagrange equation is this, which is d by dt of del t divided by del qk, about the del qk divided by the del qk dot, so we are not right about the direct Lagrange equation, but we are going to write an equation which is a general expression of this. I know that you will say that no, this is not a Lagrange equation, but listen, if you listen it carefully, then you can know about that this is an alternative. So del t divided by the del qk is equals to the gk, where gk is called the generalized force. Gk is called the generalized force. Just like there are some of the generalized quantities like the generalized there is a generalized displacement, also there is a generalized velocity, there is a generalized coordinate. So everything which can be derived from the generalized coordinate, like suppose you have a generalized coordinate qk and you take the time derivative of the qk, it means is dq by dt, then the quantity when the qk, let's imagine this is x, maybe our generalized coordinate is x, okay, and then this is equals to the generalized velocity v. So this is generalized velocity. Just like this, there is a generalized force, but remember, it is not necessary that the generalized force has the units of Newton. It's not necessary that it is a unit of the Newton. Okay, remember, this is important point, that it is not necessary. Just like that, it is not necessary that the generalized coordinate, let imagine qk, can only be x, y, and z. It is not necessary. It can be anything. It can be theta also. It can be polar coordinates. It can be spherical coordinates. Anything. It is not necessary that qk is only x, y, and z. Just like this, it is not necessary that the generalized coordinate has the unit of the Newton, which is of force. It is not necessary generally. And this is the more fundamental form. But the another expression for the Lagrange equation, which is the very famous expression, is d by dt of the del L divided by the del qk dot. It means here is a time derivative of the del qk minus del L divided by the del qk is equals to the 0. So this is the one of the most fundamental thing in the Lagrangian mechanics, and you will see that there's a difference between these two particular equations. So you will see that this is the most general form of the Lagrange equation which is written in the textbook. And what is the difference between these two things? So the difference is that this is our general form, but what happens if this particular gk force, yes, generalized force, is derived from the potential, as you know that force is equals to the negative of the gradient of the potential, and I have also discussed in one of my vector operators video that force is equals to the negative of the gradient of the potential. And what if this particular generalized force is derived from this particular expression? Then I can write gk as negative of the gradient of the potential. Okay, so I'm going to derive this particular equation from this particular equation. So we are now going to derive of this particular expression, that how from this we obtain this. So let's see here. Let's choose some another color. Now here you know that this is our particular general equation for our Lagrange, and how can we derive this more fundamental. So as I have said before, that what happen if this particular generalized force is derived from the gradient of the potential, then I can write this particular as the gradient of the potential. But the more general way to write this is in the derivative form, is the negative of the del vi and v divided by the del r, or you can say that in the generalized coordinate form it is more reliable to write it. And why I am writing this, I will give the proof in the next video. If I'm going to derive out the general expression, I will derive out that y gk is equals to the negative of the del v divided by the del qk. How I transformed it and what exactly gk expression is, so it is the matter in the next video when I derive this particular expression. But for now I'm going to show you that this gk is equals to the negative, and to prove this expression, if you are wondering that why gk is equal to the negative of the del v divided by the del qk, then this is the matter of the next video. Okay, so this next video I will prove it. I will certainly prove it. Now I have written this. Now what can I do is that I can write it as d divided by the dt, and here del t divided by the del qk dot here, and here negative of the del t divided by the del qk. Remember here the t is called the kinetic energy. T is the kinetic energy, okay, is equals to the g minus del v divided by the del qk. Okay, this is our general expression. Remember t is the kinetic energy, and here L that I've written is the Lagrange, and the Lagrange is defined as the kinetic energy minus the potential energy, as I'm now going to prove it. Okay, I've written it certainly like this. Now how can I write it? Just put it in the left hand side, and I can get it as the d by dt of the del t divided by the del q dot k and okay, and just take a negative del t divided by the del qk, and here positive of the del v divided by the del qk is equals to the 0, Now in the next step I can take out this particular common, and how can I get this like this as d by dt of del t divided by the del q dot k. Now if I take the negative del by del qk common, it is equals to the t minus v, okay, and it is equals to the 0. Now one thing I have to tell you here, this is t minus v, and it will finally become the Lagrange, but here it is only t, but in this expression there is L. What the thing happening? So you know that here I have written that v here potential is a function of the qk. Potential is a function of the qk, not q dot k, because q dot k is dqk divided by dt. So v is not a function of this, it is a function of this. This is not a good way, okay? So v is a function of qk, generalized coordinate qk, not the time derivative of the generalized coordinate qk. So now let's see next step carefully, that how I can write it. It is equals to the d by dt here, and here del divided by del q dot k, and if I take it here the big bracket sign, then it will going to be good. and here the small bracket t minus v, and here negative del divided by del qk t minus v is equals to the 0. And I know that you have a question in your mind that why I have written v here, why I have written v, why explicit I have written here v without any of the reason. So let's listen the reason behind it. I have said that v is not a function of the generalized coordinate. It means if I take the derivative of the v with respect to the generalized coordinate qk, then it is certainly going to be equals to 0. And what I will left with the expression is this, del t upon del q dash k. Because v is not explicit function of qk, it is certainly going to 0. Then why can't I write here? You understand it? यहाँ पे अगर हम v लिख भी देंगे तो there is no matter of fact because it is certainly going to 0. When you apply it, it is certainly going to 0. It means there is a no matter of fact. I can write it here. You can think also that if I put, suppose you can do the differentiation, partial differentiation rule. You will differentiate t first. Minus del v divided by the del q dash k. Okay, let me write it so that you can understand it clearly. I know that there is a mesh up thing happening. So let's write it in an again so that you can understand it. Okay. What I'm trying to tell you that why I have written here. So, okay, let's see here. Let's see here. d by dt. Okay, d by dt here. And del divided by the del qk. And here is the dot sign, del by del qk. First of all, t and minus del v divided by the del qk dash, okay, minus del by del qk, and here is t minus v is equals to the 0. Now v is not a function of qk, it means in respective with the qk not the part, it is q dot k. So v is not a function of q dot k. It means for q dot k, v is a constant, and the partial differentiation of constant equals to going to the 0. And what we are left with this particular expression, this and these are the similar things, and I've written it only to obtain a singular equation, nothing more than this. That I've written in this form to obtain a single equation in a more beautiful way, so that I can write out the final expression d by dt here, and here del L, because Lagrange is t minus v, I've written here q dash k. Oh, what this is q L, okay, del L minus del L divided by the del qk is equals to the 0. Now this is the way how we derive this. This is the way how we derive this, and this is only possible, this particular equation is only be possible if the force, generalized force that you derived is from the gradient of the potential. If there is a non-conservative force, then this equation is not going to be correct generally. But if there is a velocity dependent potential, which we are going to discuss in the next upcoming 1 to 2 videos, I will discuss the velocity dependent function. If there is a velocity dependent function also, we can write our Lagrange equation in this form, but this will be confusing here, so I will prefer you to just left it for our future videos. So now you have seen that this is our particular Lagrange equation when the force is the conservative force and the negative of the gradient of the potential. This is our general Lagrange equation. Now you know that why Lagrangian is useful, because this whole expression is only dependent upon qk generalized coordinate and not on the other Cartesian coordinates. Now it is a more fundamental equation and one of the most important equation in the Lagrange in the Lagrangian mechanics. But now let's see some applications. And remember, I've written here very important point that this L Lagrange is equals to the t minus v. This is very important to know that Lagrangian equals to the t minus v. Okay. Now maybe the video is going it very long, I think. So I think the examples of the Lagrangian mechanics is going to be in the next video, because this video become very lengthy. So in the next video, surely I will do an example on the Lagrangian mechanics on this particular Lagrange equation, because if you do the examples, your mind will just blow up that how without using of any of the constraints you can derive the different types of the equations that we do in the Newtonian mechanics with the help of the constraints. Remember, one of the most important thing that we are going to discuss in the next video is the pulley. Pulley is our very favorite when we study the Newton's laws of motion in the class 11th. It is very fun to solve the pulley problems. And you know that every problem in the pulley is associated with the tension force. The acceleration formula, if I remember, I didn't remember it exactly, but I think it is like m1 plus m2 exactly. Okay, whatever this is, I didn't remember exactly. The acceleration formula is derived from the tension, that the mg force is acting downward here, and here is the upward tension force, and here this block is an mg force, let's say it is m dash g acting, and upward tension force. Using the free body diagram, you can usually describe the expression for the acceleration. But what happens if I don't want any type of the constraints relationship? Then without only knowing about this potential and the kinetic energy, using this particular Lagrange equation, you can derive this. So in the next video, we're going to discuss about this application. So thank you for watching my video, and the next video is also going to be very interesting.